right, yeah, like you said, I'm going to talk about how your containers aren't alone, demystifying container isolation. So I'm Marina, I'm from Adara, a company that makes a hardened runtime kind of in the container isolation space. And yeah, let's get into it. This looks like there's a lot of people walking in right now, so I'll slow roll the intro so they can all get in. Anyway. What is a container? Hopefully you've heard of these if you're here at KCD today, but in case you haven't, a container is a unit that packages up code and everything that's needed to run code, including your libraries, dependencies, and configurations. It lets your code kind of run reliably in any environment. It kind of solves the "it runs on my machine" problem. People use containers because they're lightweight, they have fast startup times, and they kind of give you access to this whole environment of tools that have been built for this container ecosystem. Another answer to this question, what is a container, kind of translating that previous one to a little bit more Kubernetes terminology, we have nodes that run on a kernel, pods that have containers in them that run inside those nodes. And there's, of course, a lot of other pieces of the ecosystem here, like the control plane, the kubelet, et cetera, but we're not going to talk about those today, so they're not pictured. And to keep asking this question, and to kind of tie it back to the topic of today, what containers really are is operating system virtualization. They came out of Linux containers, which use some advanced features of the Linux kernel to create virtualization kind of at this operating system level, instead of virtual machines, which are kind of virtualization below the operating system level. Docker actually initially relied on Linux containers before they eventually developed libcontainer, which is now part of runc. So that's kind of the history of how these containers have come to be what we see them as today. And some of the key technologies that made these initial containers and the containers we use today possible are namespaces and cgroups. So let's start there. What are namespaces and cgroups? So namespaces create distinct contexts within the kernel for each container, so they each see a different set of resources. There are lots of different types of namespaces for specific resources, including process IDs, networking, etc. But they all do the same thing of kind of creating distinct contexts. And cgroups are also a Linux kernel feature that put limits on the usage. I'm going to start over. Cgroups are a Linux kernel feature that puts limits on the usage of resources, such as CPUs or memory. And in the context of containers, these can prevent things like a noisy neighbor attack, so where one container accesses the whole CPU and the other containers don't get access to any of it at all. So this might sound like some isolation, right? We're separating our resources, we're separating different things with these namespaces and cgroups. So why are we still talking about container isolation? That sounds like isolation, right? And the main thing is that even though you have these namespaces and cgroups, which are like features of the Linux kernel, there's still like the whole rest of the shared kernel with lots of functionality that's either not covered by namespaces and cgroups or is kind of below them in the stack. And this means that things like networking, things like memory, they're shared between containers. And also things like system configurations are often viewable from the container. A fun thing that you can do, actually, I should probably have done this as a demo, but on your free time, is just open up a Docker container, an unprivileged container, the default configs in Docker, and just see what you can see of the file system of your host machine. I think you'll be surprised at how many processes and services and stuff that you can still see from inside the container. So for example, an attacker could see like a vulnerable kernel version or a misconfiguration of your Docker settings that could lead to them to be able to do an attack. Or they could just interfere with the system's entropy. There are a lot of things that are actually file descriptors under the hood in Linux, like dev-urandom. It's just a file that you can actually write to, and that messes up your whole system entropy. And this doesn't even take into account bugs in the technologies of namespaces, cgroups, or the kernel itself that can let a user in a container do even more. And isolation is especially important when we have multi-tenency. So folks often run containers in multi-tenant environments, meaning containers from multiple different organizations or different users of the same organization are sharing the same infrastructure. And this is great for resource efficiency. You only pay for the computing resources that you're actually using, and other tenants pay for like the rest of the machine. And this makes it kind of pretty common in practice. Unfortunately, this kind of exposes you to some of these kind of hidden assumptions about the isolation of containers. Containers include everything they need to run an application, but they're running this application inside the same kernel as the other containers. They're kind of similar to processes inside the kernel. And this means that if other mechanisms are not in place, containers might be able to view or alter resources in other containers, or worse, the host system itself. Yeah, so that's an example of an attack there. So what we need is some mechanism in place to create this isolation. So to illustrate why we need container isolation, even more, in case you're not convinced yet, here are a few kind of container escape vulnerabilities from the past year or so that kind of led to, this seems to not be displaying properly. Oh well. That's weird. Let's see if the next slide's working. Okay. Anyway, it's not important what they are. There's different attacks in this space that can kind of lead to breaking these assumptions around container isolation. That's kind of the main point there. And yeah, the point is that isolation is hard, and we want to kind of prevent these types of attack on our system by creating kind of a better layer of isolation. There are a lot of different technologies that provide isolation, and here we break them into, I kind of like to break them into these 3 general categories, kind of vaguely aligned with the technology stack. And then we're going to talk about some open source technologies in each of these categories, so you can kind of get a sense of how they all fit together. First, we have application and service isolation, which separate workloads and APIs kind of at that user space level. Things like namespaces and C groups are kind of the foundational beginning, also fit into this category. Runtime isolation enforces boundaries in the compute environment itself, kind of a level below that with things like a hypervisor. Hardware and physical isolation creates physical boundaries between workloads, things like air gaps, confidential computing. And of course, when deploying an application, isolation probably isn't the only thing, or maybe not even the first thing that you think about when doing that. And I think it's important to look at these two, especially as we go through these technologies, so we can think of why you might use one over the other. So the level of isolation, that's the one we talked about, but also things like performance, hardware requirements, especially some of the lower in the stack isolation technologies introduce hardware requirements, compatibility with your existing workloads and tooling, and all of these different things can be important depending on your exact application, how sensitive is it, how performant does it need to be, where does it need to run, all that kind of stuff. So let's get specific. First, we'll go into more technologies in the application and service isolation space. Has a little bit of a lag. Anyway, setconf is a Linux kernel feature that restricts the system calls a container can make. So this limits the kind of attack surface within the container itself because there's less system calls that the container can access, which gives it less ways to try and break out of that container. Linux capabilities divide superuser privileges into distinct units. So this is great if you want to give a container some privileges, but you don't want to just have a privileged container, right? You can give it just the ones that it needs to do what it needs to do. SELinux AppArmor kind of provide a mandatory access control layer to the kernel that kind of just defines access control for the applications, processes, and files inside the container, with policies set for those. So all of these technologies, these application and service isolation ones, and also as well as namespaces and C groups, they work inside the Linux kernel, right? They're features of the kernel that you can add more isolation to your containers, right? Kind of create more boxes inside the kernel that kind of separate different pieces of it from your container. And they can be layered together, obviously, for better protection, but fundamentally, everything in this category, because it's working kind of on top of the kernel, there's still a shared kernel, right? So this is just kind of making, what's called, putting little layers between it and the kernel, but it's not actually eliminating that fundamental sharing of it. If you want to do that, I think we're going to talk next about runtime isolation. This kind of goes a level deeper in isolation of what happens if we actually eliminate that shared kernel altogether. The first thing I'll talk about here is a little bit different than the others. It's gvisor. It creates a container sandbox that provides what they call a user space application kernel. This is kind of cool because it provides the same kind of separate kernel for each container, but it does so in user space, which means that there's no hardware compatibility issues or anything like that you have to deal with. And it's able to prevent a lot of the known attacks on isolation while doing so in user space. So that's pretty cool. And then to talk about the rest of the kind of runtime isolation technologies, I want to step back and first explain what a virtual machine is and kind of go into that and then explain how we can use these with containers. So I think a lot of people think that they're kind of incompatible technologies, so we kind of explain how we're going to make them work together. So this is kind of a traditional virtual machine here that I'll talk about first. It has a separate operating system kernel for each workload. So to achieve this, there's the hardware, and you have a hypervisor that runs on the hardware to enable a virtual machine monitor, or a VMM, because that's a long name, to orchestrate the resources to each guest operating system. And then the VMM kind of mediates all access to the CPU memory and everything below it. So the guest operating systems are not able to actually access those resources below it without going through that layer. And this provides a really clean isolation boundary. You can kind of see how, as opposed to where you have this shared kernel, like it creates a kind of clean separation of the resources. But virtual machines, especially kind of traditional ones, can be kind of clunky and are designed more for things like dual booting or application testing on different operating systems. And it does seem a little bit inefficient to run an entire operating system just to run a single workload, right? And so what folks have done is they've designed what are called micro VMs to kind of get a lot of the isolation benefits of virtual machines with a little bit less overhead. So same kind of general design here. We have an additional container runtime layer, right, to make this container compatible. And the other thing here that's a little bit different is the guest kernel is going to be a little bit more lightweight in a micro VM system. And there's also a lot of tricks you can do if you control the whole stack, like having kind of read-only shared memory for the kernel itself. So you do have a separate kernel for each one, but there's pieces of the kernel that are the same can actually just be in memory once, right? So you're not duplicating things, and that's in like a read-only section of memory, so it can't actually be altered. So there's some kind of clever optimizations you can make to make this a lot faster and get things like faster startup time, support for container runtimes, and all of that. So let's talk about kind of different technologies at these different layers and how they all kind of fit together. First at the bottom, we have the hypervisor. The two probably most common ones, open source ones, are Zen and KVM. KVM is a type 2 or hosted hypervisor that acts as a module in the Linux kernel that enables the use of hardware virtualization features on CPUs. So in the cloud, this use of hardware virtualization features means that you need either access to a bare metal instance or pass-through of these virtualization features to your non-bare metal instance, which is not super common in the kind of popular the clouds, or it can be expensive. Zen is a standalone or type 1 hypervisor that supports both hardware virtualization in what's called PVH mode or para-virtualization, which means it can run on any CPU or in any cloud environment without actually that bare metal access. So that can be nice if you're trying to do this in the cloud. Going up the stack, we have the virtual machine manager. Some folks also refer to this as the hypervisor, but they always need to run on top of the other one, so I like to separate them. The first one I'll talk about here is Firecracker, which is a VMM that powers AWS Lambda and Fargate. It's, I think, most famous for having really fast boot times. It's kind of their claim to fame. And it kind of creates a small attack surface at this VMM layer. And that runs on top of KVM, and then you need some kind of container runtime on top of it to then run your containers. Cloud Hypervisor is another VMM optimized for cloud-native workloads, backed by Intel, also runs on KVM. Next, we have Kata containers, this is the container runtime. So now you have to pick one of those other VMMs. There's also lots I don't have time to cover today, so those are all great too. And on top of those, you run Kata containers. And then this is a lightweight container runtime that lets you run OCI compliant containers, so the containers you have today, inside a micro VM. And then, you run on top of those other layers. Another system, this one's actually more of an end-to-end than it is one of the layers, is Apple's containerization framework. This also uses a micro VM architecture. It's specifically optimized for Apple Silicon, which gave, them having control of the entire stack gave them some cool opportunities to do some optimizations here. And this gives you strong isolation even in development environments. So if you're developing in this Apple container framework, you kind of get this kind of isolation even on your dev machine, which is really great for running untrusted workloads locally. So you're looking at some vulnerabilities and want to try to see what they do, or you're doing early testing of an application where you're not really sure what it's going to do. You can still put it in a super isolated environment here. Another one that's a little bit different is a unikernel, which is kind of similar to a micro VM, but a bit more lightweight at the expense of compatibility with your existing containers. But it's much more lightweight, which is very cool. What it does is it compiles your application with a microkernel to create what I like to think of as like a single application mini kernel. So you run this kind of mini operating system thing with your application on top of the hypervisor, VMM, etc. And this is super strong isolation again, but with like a lot less of the overhead. And then sometimes, in some cases, this can even be faster than kind of traditional containers because you have so much less overhead there. But there's, of course, limitations in terms of compatibility. If you have to rebuild your application, you have to then rebuild the kernel, which is a little bit inefficient. So that can be pretty tricky. And also, it's not necessarily compatible with every environment you want to run it in. But for especially things like IoT, kind of edge devices type stuff, this can be a really lightweight option for isolation. So in summary, runtime technologies, except gvisor, which I also kind of categorize here, have a separate kernel, and gvisor has a separate user space kernel, so similar idea, per container, which provides kind of a strong security boundary. That isolation boundary is kind of like in a really strong place around the container, and without relying on those kind of kernel mechanisms. Of course, you should probably still use those kernel mechanisms, right? There's no need to limit yourself in terms of what you can do to secure your applications. But some of these technologies come with performance or security trade-offs, or have hardware requirements that you need to start thinking about in order to get them deployed. And so that's kind of the trade-off you have to make when figuring out if this is the right decision. But if you need more isolation, I think looking into these technologies is probably worth it. Finally, we have hardware and physical isolation. So this is for when you really want to make sure that stuff is not going to be able to interfere with each other. The first method, I think the first one that probably comes to mind for folks, is an air gap, where each container is run on a completely separate machine, generally even completely separate from the internet, right? So you have it running in a place where stuff really can't interfere with it. And anything coming from the internet has to kind of pass through some sort of interface to get there. Great for isolation, obviously, because not only do you have no shared kernel, there's no shared hardware, there's no internet, great isolation. Unfortunately, and this is great for kind of edge, highly secure environment type stuff, but it can be kind of expensive or impractical because you actually have, not only separate hardware, you have to deal with this interface layer and all of that. But of course, very isolated. And we also have confidential computing. So the idea with confidential computing is you have what's called a trusted execution environment, or TEE, which is a piece of hardware that kind of runs alongside your CPU, and you can run your container inside the TEE. This is generally done alongside a microkernel setup. So you have the kernel run inside the TEE, so it has everything it needs to run. And examples of this for the container ecosystem include Constellation and confidential containers, which are both open source kind of CNCF projects that work in this space, kind of providing this. Again, very strong isolation because it has this hardware component that your container is running on. It's separate than it running on the CPU. You get things like encrypted memory, kind of encrypted data in use. But you do need access to this hardware chip, and they have somewhat limited number of containers you can run per chip. So this can be a little bit tricky to do, probably best for when you really need an even stronger isolation. So here's a quick summary of the isolation mechanisms we've discussed. We have a bunch in the application and service isolation. Those are the ones running kind of at the top of the stack in this Linux kernel. We have runtime isolation. What if we separate the kernels from each other? And then we have hardware and physical isolation, which is, we don't even want the same hardware between our different things. We want it really in its own space. And the technologies talked about there. So just a quick summary. And then I'm going to move on really quickly to, because it's 2025, so here we are. We're going to talk about AI. Specifically what I mean is we're going to talk about GPUs, right? And I think the AI workloads have meant that people have been seeing a huge increase in the use of GPUs by container workloads, especially for inference, which I think is more relevant here. I think folks doing training often have access to their own machines, their own GPUs, but for if you're running an application that just has some AI usage, you're probably using inference, and inference runs better on GPUs. So why are we talking about isolation and GPUs? GPUs are expensive. I'm sure folks are aware of that. And so we want to optimize the usage of our GPU and make sure we can use every second of that GPU time that we can. So we want to make sure that all of our different containers running on our system can share this GPU. Unfortunately, GPUs weren't really designed for this, right? The things like memory is not always cleared between different processes running on the GPU. They're really designed for speed, right? That's the whole point of a GPU. And I think some of these multi-tenency on GPUs is a little bit new and evolving. So I'll talk about some of the stuff that exists today, and we can kind of imagine a future where we can do this maybe more efficiently too. So here's a bunch of strategies for sharing GPU among multiple containers, kind of roughly in order of where they fit in the stack. So at the top, we have GPU time sharing. This includes things like NVIDIA vGPU or Intel's GVTG, sorry, which allows for things like context switching between containers. I don't say that aloud that often, sorry. And this provides software level isolation. But it doesn't always do things like clearing memory between applications, which can be a big problem, which means that like if you have multi-tenancy, you have two different applications that don't know about each other. One of them could be able to read the memory left over in the GPU from the previous one. And we've actually seen attacks on GPUs for even just in things like browser rendering, where one browser tab might be able to see what was rendered in another browser tab because they're run on the same GPU. So this is kind of a tricky thing here. Another thing is that vGPU specifically actually requires that you buy a license per GPU that you use it on, which can be a little bit prohibitively expensive if you're doing like a at-scale cloud application. Next on the stack, we have GPU partitioning, which includes things like NVIDIA multi-instance GPU, or MIG, and AMD's MX GPU. So what both of these do is they kind of split the GPU into slices at the hardware level. So you could provide like a slice of the GPU to one container, a slice to another container, etc. And then finally, PCI pass-through passes an entire GPU to a VM. This is the best for isolation because you don't have to worry about the GPU doing the partitioning properly, but you don't have to worry about bugs in that. So it works for VMs, of course. You have to give direct access. But of course, you're not really splitting time on your GPU. You're just kind of giving the GPU to this thing, clearing the GPU out, giving the whole GPU to this thing, which again provides you better isolation, but maybe not as much efficiency. So in summary, yeah, we have GPU time sharing, which does software isolation. You might have to worry about some shared memory pieces. GPU partitioning, PCI pass-through both hardware level. GPU partitioning actually splits the GPU. PCI pass-through passes it up to your containers kind of one at a time. So, and I think, so just kind of taking a step back here from the specifics of how you actually share a GPU between your containers. I think we talk about why does this matter? So container isolation, I think, is especially important when we're talking about adding GPUs to the mix. Because they don't have as many isolation boundaries internally, we've been seeing, especially in the past year or so, I think 5 or 6 different vulnerabilities in different GPUs because people are starting to try and run multi-tenant applications on them. And so without careful design, containers with access to the GPU might be able to read information from other GPU workloads, which is especially bad if this contains sensitive data like model weights, user data, or other things like that you're running on this GPU. So the point here really is that you need to make sure that whatever you're doing for container isolation takes into account pieces of the hardware like the GPU and how that isolation actually applies throughout the stack. And isolation mechanisms from earlier in the talk that work at the hardware or kernel or right below the kernel have an advantage because they can be a little bit more hardware aware. Right? If something is running inside the Linux kernel, it has to be compatible across hardware, so it kind of is definitionally a little bit less aware of the full stack here. And I think that this will improve over time. I think that as inference becomes more common, as new GPUs come out, it takes time to develop hardware, and so this will keep getting better. And hopefully we'll find a similar set of open source, open standard ways of doing GPU isolation that kind of fit in with the whole kind of world that we have today of CPU isolation. So bringing it all together, containers are operating system virtualization. That's what they do. They use namespaces, they use C groups to kind of create a view on the operating system, but they're still kind of running like processes on your operating system. Multi-tenant applications require more isolation because when you're having that shared kernel, you have to make sure that they can't impact other containers or the operating system in ways that you don't want. Container isolation strategies include things at the application and service level, things running on the kernel. You have runtime isolation, and it takes a step below. How can we actually have a separate kernel per container? And hardware and physical isolation, which takes it one step even further to see what happens if we have separate hardware for each of our containers. AI applications need both container isolation and GPU isolation, and I think we should all be talking more about how we can get that GPU isolation to be easy and seamless, like some of these container isolation strategies are already. So thank you. I think we have a couple minutes for questions because I probably talked too fast. So thank you all.